Today we will start with actually handling GIS data. So we will start with vector data. So for whatever I'm talking about today is available on this link, bit.ly/vector-python. If you can download now, great. Otherwise, you can note down this link and you can download this later. It will have the slides and the Jupyter notebooks. Okay. So if we talk about GIS, how to do vector processing, raster processing, or any kind of GIS analysis, you could analyze GPS data, you could do web mapping, you could do time series analysis, many things. So Python has many packages. Some of them are listed under this website called PyPy. We call it PyPy. This is Python Package Index, pypi.org. Until yesterday, there are close to 613 different packages to handle GIS data. It is very difficult to teach all these 613 packages. Also for vector data, there are many different packages. The primary, or you could call the parent package, is GDAL OGR. This is one package, GDAL. It has different pronunciations, Goodle, GDAL and all that. You can pronounce it any way you want. This comes with a sub package called OGR. GDAL deals with raster data. Today we will talk about OGR, which deals with vector data. Now this is a parent format. It handles all different types of vector data. So it is very exhaustive. So they've built a new wrapper around it called Fiona. It is slightly easier to use. And if you're only interested in working with shapefiles and not other vector data, then PyShape or shapefile is the easiest. So these packages are primarily for reading and writing vector data. Similarly, there are another set of packages called GeoPanda, Shapely, PySal. They are all for analysis of GIS vector data. And then you've heard about these packages, GRASS, QGIS, ArcGIS. They all have their own Python packages for doing vector handling. All of them are mostly under active development. That means if you look at the last release, generally some packages people develop and then it fades off with time. But most of the packages that I show you here today are under active development. We will try to focus on these two, GDAL and GeoPandas, which have been released in July itself. As I told, all these packages are meant for different things. You can select a package for your requirement, but learning OGR would be very beneficial because it allows you to handle all kinds of vector data. Further, there are several more categories of Python packages like space-time analysis, GPS data analysis, projections, mapping, network analysis, and all that. So there are many different Python packages. We will talk about two packages today, which is OGR and GeoPandas. So what is OGR? OGR is a translator library for vector geospatial data formats released under an open source license. These terms are important. Translator library. Initially, GDAL OGR was developed with the idea in mind that it should translate from one file format to another file format, from shapefile to KML to any other file format that you may have worked with. So it is called a translator library, but it does much more than that. It is an open source, it is under open source license, so you could use this library, develop your own software, and possibly one day sell it also. So it is released under a very permissive license called LGPL, and that helps you use this in any context. It presents a single vector abstract data model to the calling applications. Now, when you read any data format, you basically get one variable which can then be worked on and then saved as another file format. So inside the program, there is a single data model irrespective of what type of file you are inputting. The beauty of OGR is that it comes with a set of useful command line utilities. Now, if you don't know Python, if you just want to use OGR to translate from one file format to other, there are set of command line utilities. You just open your command prompt, type OGR to OGR, and then you can translate any file format to any other file format. GDAL OGR was initially founded by this guy by the name Frank Warmerdam. But now he's working with Google and not an active maintainer. These people have come into the picture, even Roart, Howard Butler, and there's a very strong team which looks into this. This is the webpage, jidal.org, and the software GDAL is used by, GDAL OGR is used by nearly 107 different softwares. So it is a library which is used across softwares. So initially, if you talk, I give this example that ArcGIS, previous to version 9 point something, who had their own library for reading and writing raster and vector data. But GDAL became so strong and so powerful that they ditched their own library and moved to GDAL. So the package that you buy is actually using open source software at the backend. So if you go to this link given at the bottom, you will see that on their website, you see that all popular softwares, including ArcGIS, QGIS, Google Earth, Saga, even those 3D, Skyline Globe, everybody uses GDAL. This is a nice tweet recently by this guy, Noel Dawson. He is one of the active maintainers of QGIS. That it is a reminder that even Roalt is ever hit by a bus, the whole spatial community is doomed, because this guy, even Roalt, is one of the primary maintainers or developers in GDAL OGR, and they are doing very good work in developing this library. OGR supports all known file formats. Their website says 95. Every file format you have possibly heard, you can work with in OGR, including shape files, KML, Elvis file, Saga file, MicroStation, DGN files, GeoPackage, and different databases like Oracle Spatial, PostGIS, and so on. So this is all generic information. Now let us get into actual Python. So what I want to highlight is that this course we are using Anaconda, the distribution. If you have not yet downloaded it, you should go to your laptop, go home and download the Python 3 version of Anaconda. Anaconda is a distribution. There are many such distributions. We are using this because it comes along with many other useful packages like NumPy, Matplotlib. It doesn't include GDAL or GeoPandas. So depending on whether you have a 64-bit system or a 32-bit system, please download this, install it. And then this is the web page for GDAL, which we are using today, and this is the web page for GeoPandas. Both of them have very good documentation. So if you think that some things I have missed out today, you can go there and look at the example code and possibly try to do it yourself. So once you install Anaconda, do I have it here? Yeah. So let me start from the scratch. If you have already installed Anaconda on your start menu, you will see Anaconda prompt. Go there, activate your environment, whatever environment you have. I have an environment called test, and this is very large. Let me reduce the font. So I have created an environment called test, and if I say conda list, it lists all the packages that I have installed here. What I am interested in seeing is that it should have Jidal installed. So you see the name Jidal here and GeoPandas here. These are the two packages which I have installed. How to install this? Simply open your Anaconda prompt and type conda install and then the name of the package. So conda install Jidal is for installing Jidal. Conda install GeoPandas is to install GeoPandas. These versions keep getting updated. The version for which the tutorial is made is Jidal 2.3 on Python 3.7. It may not, the tutorial may not work on Python 2. So also, this is a warning that do not try other methods. Jidal traditionally has been a nightmare in installation. If you are using pip or any other virtual environment or something, it can be a nightmare in installing Jidal. So I do not suggest any other way apart from what I have shown you. Simply go to the Anaconda website, download this, install it, start your Anaconda prompt and type conda install Jidal and conda install GeoPandas and get it done. Do not try any other technique. There are many other techniques. I would not suggest any other techniques. And if you mess yourself up, don't worry, you have QGIS to save you. Inside QGIS, there is a Python console. Some of you may know it. Let me start QGIS. You all have seen QGIS. Inside this menu option which says plugins, there is an option which says Python console. And this is where you can type your Python code and work with it also if Anaconda doesn't work. This is the last resort in case nothing works. So why two libraries? Why not stick with OGR? OGR is the core. It helps you read and write vector data, nothing else. It doesn't allow you to display it. It doesn't allow you, if it has dependency on other libraries for projection changes. It has dependency on other libraries for displaying and all that. So GeoPandas is one library which integrates these different things. This is also open source. It makes your life easier. It basically extends this library called Pandas. Some of you may have heard Pandas. Pandas is primarily used today for data management, tabular data management, being widely used in machine learning and SQL type of things where you want to do, or database type of things where you want to do. So GeoPandas extends this Pandas. So most of the Pandas operations are also available. You can do analysis, spatial analysis using this library Shapely, which is integrated in GeoPandas. File access, that is reading writing, instead of using OGR, it uses Fiona. Fiona is built on top of OGR. And for displaying the data, it uses two libraries called Descartes and Matplotlib. So you don't have to worry about installing them separately. If you just write conda install GeoPandas, that should install everything along with it. So that is one library to do everything. The version that we'll be working on is 0.4 on Python 3. This is the latest version. Of course, they keep updating every few days. So that is with respect to slides. We will directly start with our Jupyter notebooks, where we talk about OGR in one and GeoPandas in the next. Again, if you've come late or joined now, you can go to this link and download the slides and the materials that we are showing today, which is bit.ly/vector-python. Also, if you're watching this on YouTube, you can just type on the comment box whether you're able to download or access this link. Also, it would be great to know if the audience knows GIS or Python. So let's ask the studio audience, how many know GIS? Everybody knows GIS? उठा लो हाथ. अभिनंदा, तुमको नहीं आता GIS? आता है. How many know Python? Very few. All of you know Python. Very good. So most of you can follow this thing. So yeah, you can write down this link. You can access the data and slides later. Just a fair warning, this data that we are using, it is only for demonstration. Please don't go around claiming that this India boundary has come from ISRO and it is the correct one. It is only for training and demonstration, and we do not claim any accuracy of the data. So there are some data sets we are using, highways, country boundaries, state boundaries. These are only for demonstration, and it doesn't mean anything in real world. The content has been greatly derived from people on the internet, good people on the internet. So Kiss Garage, this lady, she's done some, in 2009 itself, she published a very good tutorial on JEDAL and OGR, and since past 10 years, that has been the de facto standard to learn OGR. Earth Lab, they've developed some good content on GeoPandas, and these are the places where the data has been derived from. So I started Anaconda, I activated my environment. The next thing I want to do is start my Jupyter notebook. Now, initially, sir may have shown you that you can start notebook directly from here. I prefer it starting from the command prompt. Why? First thing, when you download the content, so you type this URL bit.ly/vector-python. It will take you to a GitHub repository. All you have to do is click on download zip, and it will download this folder to your local drive. So I have already downloaded it. I keep it on my desktop. You will see there are two Python notebooks, OGR and GeoPandas. This two we will work on, and this is the data folder where all the shape files that we are going to work today are kept. Yes, also in case you do not have Anaconda installed and you want to do this now, if you open this link, there is a button which says Launch Binder. There's a very good project going on these days called My Binder, and the notebook opens up in a Docker container, basically a virtual environment, and you could run the notebook directly along with me on your laptop without installing Anaconda or anything. So it opens up a new environment. You can directly open the notebook and start running the cells. Great. Now, let us so why I prefer this is because it allows me to go to the folder where my data is kept. So my data is kept on the desktop inside this folder called OGR, and then I start Jupyter notebook. So there are some issues starting notebook in D drive or other drives when you go from this way, from the start menu. If you want the notebook not open in C drive somewhere else, there is a workaround, but it is not straightforward. So simply, if your data is kept in D drive or E drive, you simply start Anaconda prompt from here. Do CD, go to your drive where your data is kept, and type Jupyter notebook. Okay, so I've started Jupyter notebook. I have my two notebooks. Let's start with the OGR notebook. OGR is part of the okay, so let's take some questions on YouTube. Somebody is asking, can we do this on Spider? So Spider is a IDE, integrated development. There are many IDEs like PyCharm, or anything else. So anything which opens up IPython notebook is sufficient, or a Jupyter notebook is sufficient. It could be Spider, it could be PyCharm, it could be Anaconda. Jupyter has come with a new thing called Jupyter Lab. Anything which opens a IPYNB file is great for me. It has no dependency on using Anaconda. I'm assuming that most of you are starting it for the first time. That is why we are recommending Anaconda. Otherwise, there's no specific reason. If you're happy with Spider or PyCharm or any other, great. Okay, great. So that was the only question. Maybe Kamal sir didn't talk about what a notebook is. Let me just give you a very brief intro of what a notebook is. Notebook allows you to write some text in these cells called markdown. And if you click on this cell, it becomes code. So there are primarily two types. There are actually 4 types of cells. Primarily, there are 2 types of cells. One is a markdown, which is a non-code cell, and one is a code cell. So I write some literature. Okay, the tutorial is designed to give you an overview. And this is a code cell. How do you run a code cell? You click on that cell and you click on run. If it doesn't give an error saying, it means that OGR is installed and it is working fine. Also, Notebook allows you to not only run Python commands. So I want to run something on my computer, something like dir, something that you do on your command prompt. So you can simply append exclamation and it will run things that you run on your command prompts. These are especially useful when you want to do a Conda install or something directly from a notebook. So what you're doing here is whatever you write with an exclamation prefixed is running on your normal command prompt. Okay. So as I told you, there are command line utilities which come with OGR. OGR to OGR is one. Similarly, there's one called OGR info. Let us run this. This is a command line. This is not a Python utility. This is not a Python line. You see there is an exclamation here. It means that it is a command line code that I am writing. And just printing out all the supported formats. So you will see all the formats it supports. It includes KML, GeoJSON, shapefiles, and so many other different formats. I'll just clear some cells because the output is very large. Okay. So to open a file in OGR, the first thing that you need to do is to select a driver. Now each file format has a unique driver. Okay, so let's say shapefile has a driver, a KML has a driver. So if you go to their website, vector drivers, on JDAL website, there is a link which says vector drivers. You will see all these different file formats. If you click on the file format you are interested in, it will give you something called a driver short name. This is the code which is used in your notebook to get the driver. If you type anything else, just shapefile or ISRI no space shapefile, it will give an error. Okay, so you get the corresponding information from their page. You can go to the corresponding, if you want to open, let's say something else, a KML file or something, Control F KML, then the driver short name is just KML. Okay, so you must know what is the name. So once I say ogr.get driver by name is shapefile, it creates a driver. Now one general thing which you could know is JDAL OGRs is originally written in C++, and they use something called a Swig. Swig is another program which allows you to write wrappers around C++ code. So what we are using here is basically JDAL, which is written in C++, provided to us or provided to Python by a Swig wrapper. So many places you will see something like a Swig object. basically it is saying that the program, this code is working, and object is generated, which is OGR object is generated, which is provided to you through Swig. Next, let us open some files. So inside the data folder, there are many files. To start, we'll use a file called sites. So there is a file called sites. Let us just see the file in QGIS first. What is this file, so that we can correlate when we run the code. So if I open this file sites, it is of what file format? It is a point file. It is in a projection system called UTM-12N. Is somewhere in the state of Wyoming in US. It has some attributes, ID and cover, and it has how many points? It has, I think, 42 points. Okay. So this is the data. Now what happens if I open this in OGR? I say driver.open. Now you see this driver comes from here. So you have to predetermine what file format it is, create a driver according to that format, and then open the file. Then you have to give a code. 0 is for reading, 1 is for writing, and print DS. Now this line was your data source proxy of Swig object will only come when the file is read correctly. If you by mistake give a wrong file name or a wrong path, or some other issue happens, then it prints none. So generally it is a programming practice is that we do if DS is none, print file could not be opened, something. Okay. So if I change something here, it says, so this is a general programming practice that if your driver is not created or your file is not opened or some layer is not opening, you first check what is the content of this variable. If it is none, that means that the file could not be opened or the driver could not be created, and so on. Now, the next thing is we get a layer. Now, different file formats allow different types of things. For example, somewhere I saw in CAD, you could save a file where all points, lines, polygons, everything can be included. In shapefiles, that is not allowed. You can only have a point shapefile, a separate file for line, a separate file for polygon, and so on. So since OGR is made for, it's like a Swiss knife, works for everything, this get layer is more applicable in other file formats. For shapefile formats, it is not much applicable, but since it has that a step, you have to do it. So you have to first create a driver, open the file into something called a data source. DS is a data source. From the data source, you get a layer, ds.get layer, and when you run this, so it gets the features into something called a layer. Now all your features is there in this variable called layer. If you say layer.get feature count, it tells you the number of points in that layer. So similarly, if you had multiple files, you could write these 3 lines and you could get the features from all of them. If you want the bounding box, you can say layer.get extent. Extent is equal to this, and yeah, so it is actually a 4 element tuple. So if I said extent colon comma extent, so this is the variable extent. It is a 4 element tuple. The first one and the third one, 0 and 3, is the upper left coordinate. Sorry, the first and the last one is the upper left coordinate, and the second and third one is the lower right coordinate. Now, some people students may have this doubt, what is a bounding box? So let us forget about point line polygons. Let us give you an overview of what is a bounding box. Now, given on the data type, so if you have points, the most extreme left-hand side point, the most extreme right-hand side point, and the most extreme top and bottom points form the bounding box for a point layer. Similarly, for a line layer, whatever is the topmost extent of the point of the vertex of a line or the bottommost vertex of a line, similarly left and right, this corresponds to the bounding box. Similarly for polygons. So when you print this extent, you are basically printing the upper left and the lower right corners of that area. Now, what is this coordinate? This is in, as I showed you, it is in UTM, that is, it is in a projected coordinate system. Hence, these are in meters. This is not in decimal degrees. If you had a file which is in lat long WGS84, that is EPSG4326, then this would be geographic coordinates. Okay, also something to note is, just to revise, is that for each feature you have one row in your attribute table. So if I have 3 points here, there will be 3 rows in your attribute table. Something which you all know, but just to remind, because once you start reading these features from the layer, you should expect that if you have 42 points, then you will have 42 X and Ys and 42 rows in your attribute table also. So how do I get these or how do I read the geometries or the attributes? So layer is the variable which has the content. You say layer.get feature, and if there are 42 features, then the number starts from 0 to 41. Let me run this. It says here I have selected the first feature, which is the 0th feature, and I'm getting the attribute named ID. There were 2 attributes, ID and cover. So I'm just printing ID. If I want cover also, I just copy this, comma, so it had second attribute which was cover. So for the 0th feature, the ID is 1 and the cover is shrubs. Similarly, for the last feature, that is the 41st feature, the ID and the cover is 42 and grass. Okay. So similarly, you can, if you know which feature you are selecting, you can specify this. If you don't know, then we will write a loop and read all the features. Okay. So how to get the next feature? Now it is similar to a file pointer. If you know programming, you open a file, the file pointer is at the start, then you read or you write things, and then the file pointer is at the end. So you want to read at the beginning, you reset the pointer and all that. So similarly, here at the beginning, it is at the, you say, it is at the first field. If you say get next feature, it prints the first one in this case. If you run it again, it gets the next feature, that is 2, 3, 4, 5, 6, and so on. We could write a loop around it. We could say till the feature, the variable is alive, get the field ID 1, destroy it, and get the next feature. So it will just keep getting the next feature, printing the field ID. Let us also print the cover along with it. And let's say what. So till 9 we had read here. So from 9, 10, 11 till 42, it prints all the features and its attributes. Okay. Like this, you could change this loop to read only sections of your shape files, or you could do something like, okay, print all the covers for features from 10 to 20 or things like that. So you could use this concept to write different logic. Okay. Now, so we've read till the last. So by doing next feature, you've reached the last of the file. Now, if I again say get next feature, I get an error because the file pointer is at the end of the file. So I have to reset the file pointer. To do that, there is something called reset reading, layer.reset reading. You do it once again. Now you've reached to the top of the file, and then you do next feature and you run this code. You will again start from 1, 2, 2, 1, 2, 3, 4, and so on. Now this get field by default returns the data type of the attribute. So if the attribute is text, it returns text. If it is double, then it returns double. If you want to, there are two other things. There is one get field and there is something called get field as string. This will help you return the value as a string. So depending on your requirement, you could use whatever function you like. Now, till now, we have only been reading the attributes. What about the geometry? I want the x and y of each of the attributes. For that, from each feature, you have to get the geometry reference. Now, currently, we are at feature number 3. So if I say feature dot get geometry reference, it gets the geometry for the third feature. It puts in this variable geometry. It gets then this variable geometry has multiple functions like get geometry type, get x, get y. So these functions are used to get my x and y's and get the geometry type. Now, what do I mean by geometry type? There are huge number of different geometry types which OGR can handle. While preparing this, I came to know there is something called 1D, 1.5D, 2D, 2.5D, 3D, 3.5D. So there is 0 dimension, 0.5 dimension, 1 dimension. So there are many different, you may have seen in ArcGIS or something, multi-line strings, multi-polygons. So OGR can handle all of them. The idea is that if you use the basic ones, which is point, line, and polygon, they are the geometry types 1, 2, and 3. Okay, and then there are many others. I forgot to put that link of that C++ page where all of them are listed, which you will never be using, but that thing is there. At the end, if you want to do memory management, if you have very large files, then you would wish to destroy the variables like feature and data source. But these are only required when you're dealing with very large files, otherwise not required. So let us do something. Let us write some program to print all the attributes as well as the geometry for all the 42 different features. So let us first do reset reading. Then let me create a loop while feet, something like while feature, get next feature and all. Let's run this. Now it works. Okay. Let us read it again. So So what I'm doing here, I've again opened my file, taken the layer. Now I'm starting at the top of the layer. For each, I take one feature, I read its geometry reference, get the X and Y, get the fields, ID and cover and the coordinate, and I print it. And I do that for all the 42 different features. So get next feature kahan hai? Now let us run this. So now what I am getting is for each of the features from 1 to 42, it prints the ID, it prints the cover, it prints the X, and it prints the Y. Okay. Now you can use this, write your own logic here. If you want anything on the left hand side of this latitude or top of this latitude or left hand side of this longitude, things like that. So you can write your logic based on these values, X, Y, ID, and cover. So that is about OGR, which I want to tell you. OGR this is not even 1% of what OGR can do. I am just talking about reading a file. It has multiple options for writing a file. So there are, all this is available online on this tutorial by Chris Garrard, by that lady Chris Garrard. The slides are linked here. She has given some assignments also. You can try this. Also, there's a very nice web page called Python OGR Cookbook, and you could try these examples and get more idea of what are the different things you could do in OGR. Okay, that is about OGR. Let us close OGR and let us go to GeoPandas. That is more interesting and more easier to use. It can do more things. Okay, so GeoPandas is a more recent library. It is not as old and all, not as well established as GDAL. GDAL is very old. It goes back, I don't know the exact date, say 98 or something, but it is very well established and very robust. It will hardly be occasions where you see that OGR is not working or GDAL is not working. But that is not the case with Pandas. Pandas is a more newer thing. It does fancy stuff, but then you get into different problems that we'll see later. Okay, so how do you import GeoPandas? You just say import GeoPandas. As a shortcut, we are putting an alias. Kamal told you about aliases yesterday. We'll be using matplotlib, and we will use somewhere down the line pandas also. So that is required. Next, let us read the same file, sites.shp. Now, see the difference. If I say this is the variable name, plot locations equal to GPD, that is GeoPandas, the .read file, and then the name of the file. Okay. And in this one line, basically I have read the entire file. All the IDs, all the covers, all the geometries for all the 42 different features in just one line of code. OGR in OGR you would have to write, get a driver, open the file, get a layer, and get individual features, and then write a loop. So GeoPandas makes your life little easier. Okay. Now you see some formatting here. It's in gray, and then this header is in bold and all that. This is not the default print. Basically what gpd.read file is doing is it is reading the data and creating what is known as a data frame. Okay. Pandas uses the term data frame. GeoPandas uses the term geodata frame. Okay. With the data frame, there are many functionalities, built-in functionalities. Just in NumPy array, like in NumPy arrays, you have NumPy array.min, array.max, array.reshape, array.transpose. Yesterday, you saw many of them. Similarly, in geodata frame also has many different functionalities. Like the print function in plot in our data frame is made such that it prints in a formatted output. Okay, now, so for example, there is a built-in function for data frames called head. There are two functions, head and tail. What does they do? It prints the top n lines. Okay, so if you say head 6, then it prints the head or top 6 lines. If you say tail 6, then it prints the bottom 6 lines. Okay, very simple, very easy. How do I know how many rows and columns this has? Plot locations dot shape, similar to NumPy. So plot locations is the variable. 42 is the number of rows, which is the number of features. 42 points. So 40. So if I have to get number of points, I say plot locations dot shape 0. If I want to get number of attributes, it gives 3. So there is ID, cover, and geometry. So geometry is also a column here. To get the extent, plot locations dot total bounds. No extend 0, 1, 2, 3 वो सब कुछ नहीं करना है. ठीक है. Similarly, if you want the projection system, you just write variable name dot crs. If you want the geometry type, it will tell the geometry type for each feature. Okay. Now, as I said, many file types allow features of point, line, polygon to be saved in the same file. Shape files do not allow that, but so here it prints the geometry type for each feature. Okay. Do we have some questions? Let's take some questions. Oh, very good question. Where can we learn basics of Python? Anybody would like to tell? There are many sources. Generally, people recommend ThinkPython. ThinkPython is a free and open source book. The PDF is available directly. Just Google ThinkPython, and a very nice, well-developed book in PDF form is available. And you do not need to know everything. To do what we are showing today, I think the first 6 chapters, that is still conditional, recursion, probably strings, list, maximum 10 chapters are enough to understand what we are doing today. If you think 6 chapters are big enough, then there is a book developed by an Indian. He's a scientist at Inter-University Accelerator Center in New Delhi. He has developed a book called Python for Education. This finishes Python in 2 chapters. Chapter 2, Chapter 3. Khatam. Isme to NumPy bhi, so they'll tell NumPy also in 2 chapters. So this is a very thin book. For those in IIRS, you can go to the library. It's a very thin book. You can buy it, I think, ₹50 or something. And the PDF is available legally, free of cost, on the internet. So these are different books which you can use for learning Python. Apart from that, for new age learners, there is a website called Kaggle where you do big competitions and all. But you say kaggle.com/learn, and here you can interactively learn Python on a web interface. No need to install anything and all that. I found that to be very simple. So you can directly click on these cells and run the output and all that. So this is an interesting place. Otherwise, there are so many places. Stick to any one. That is my suggestion. There are so many places where you can learn Python. I would suggest you stick to any one. Okay, the GitHub link is, you can just, sorry, I have it on my notepad, I think. Yeah, this is the link again. So for those who've joined now, just type this on your browser and you should be able to access all the things. Yeah, Rahul is saying he's not able to run feet is equal to layer dot get next feature. That is because you've reached the end of the file in OGR and you have to do a get next feature. You have to run this line once, feet is equal to layer dot get next feature, and then this starts working. So even after doing layer dot reset, you have to get next feature to come to the first feature. Okay, then you can write a loop where you can get PPTs, data files, everything is there on the GitHub link. Go to this bit.ly link, all the things are there. What is this 3 when we, or what is this number 9? This is nothing but the attribute. If you add this file in any GIS software and you open the attribute table, the number getting printed is this attribute ID. Okay. Silly. Some questions now. Let's get back to GeoPandas. More interesting stuff. Okay, so in OGR we only saw how to read the attributes, how to read the geometry. That you can do in one line in GeoPandas. gpd.read file and then plot locations. It prints all the attributes, prints all the locations. Fantastic. Job done. But what more? I want to visualize them. Simple. Variable name dot plot. Kuch nahi. No cartopy, no matplotlib, no base map, no till 2. If you wanted to do this 2 years back, you would have broken the computer. Life has been so easier, made so easy with GeoPandas. So plot locations or the variable name dot plot, and it just prints all the points in a figure. Of course, it is not very aesthetically looking nice, but then that is what we are going to do next. We are going to make it larger so that the coordinates are more visible. I know that there is an attribute called cover, which has things like shrubs, trees, and all that. So I can make a categorical map with points having different colors based on their cover type. I want to give a legend. I want to make big circles, marker size. I want to show it in shades of orange. I want to set the title. So after you run this, let me just hide some things which you don't. Now it's looking good. So I say plot the variable based on columns, based on a categorical input. Legend is true, that prints the legend. I want it in shades of oranges. So from light orange, nearly white, to dark orange, which is nearly black. And I get my map. I want, let's say, a smaller map. This is too big, maybe. Yeah, nice. So so this legend gets automatically placed so that it can have least overlap with the elements. This is the title. So what does this code do? You write your variable name dot plot. You specify you want categorical outputs based on a specific column. You want the legend to come. You want this size to be large. You can make it 100. It will grow very slightly. So this number is based on how big small you want. This C map, this is called a color map. Okay. Now there are different values for color maps. You could give grays, purples, blues, greens, oranges. You could give from YLOR means from yellow to orange. I don't know what BR means. Yellow, orange, red, purple, red, red, purple. So all these codes you could use. So let's say I want something like this, purple, blue, green. So I just say purple, blue, green. So you can use these. There are many others. ये तो एक simple. This is one image. You go to this matplot library, search for matplotlib color maps. There are hundreds of them. Sorry. Never mind. Okay. Yeah. So there are hundreds of these color maps. We'll not go into details of that. Also, there are different types of markers. So here we didn't specify a marker, but if we want it in something like star, we give asterisk. And then there are again hundreds of different types of markers. You could write a dot to get a point, O to get circles, all these different types of symbols with these different types of codes. Okay. So all different types of visualizations are possible by specifying marker size and color maps and all that. So here I have put stars with an orange to red color map with a marker size of 65. And this code is similar to the previous one. Okay. Now, something which I encountered while running this, when you start directly from Anaconda notebook test, you would get this error when you want to reproject certain things in GeoPandas. So I've raised this issue, probably they'll solve it sometime later. But if this cell works, if you get these outputs, you'd have nothing to worry about. If you get an error here, then you have to look at this this URL hyperlink here, and there is some workaround you have to look at that. Okay, so we saw how to read a shapefile, how to make a plot of it. Can we read two shapefiles and make plots of it? Of course, here we've read a road, a linear file, and plots, which is point file, and plotted them together like this. Okay, so you can take polygons also and plot it again. Okay, same concept. You read the file, gpd.read file, into roads.plot, plot locations.plot, which is the previous sites one. Specify what color, what size, and all you want. Specify a title, and you get the output. Okay, very simple. Now let's go to more complex stuff. Now, what if I want to reproject this data? Currently, this is in UTM. I want it to be in lat long, WGS84, or I have some other data and I want to reproject it and show it. So this has some very powerful CRS. CRS stands for Coordinate Reference System. CRS transformation options. So what I am doing here, let me first run this and show you before I explain what this code does. So let me run this. What this code does is, I have three different files here. One is the land boundary. So the black part is, you see the land on Earth. Then there is graticules, these fishnet, you call it in ArcGIS, in grid they call it in QGIS, graticules they call it in GeoPandas. So these lines of longitude and latitude are displayed, the landmass is displayed. Then there are three cities, New Delhi, London, and Washington, which are displayed in green. But this is not interesting. Using the same data and by reprojecting it in a projected coordinate system, I can also display the map in this format. I have simply taken the same data and projected it into a projected coordinate system, which is Robinson. You could use Mocator, you could use any other projection system. So how do we do this? To do this, let me first show you the data in QGIS so that you can appreciate what GeoPandas does. So I have a file called land. This is nothing, it is a polygon file, very simple. Then I am using something called graticules. These are nothing but your fishnets. Okay. And finally, I have something called a bounding box. This is simply a polygon which covers the whole area. Okay. I'm using these three to create this kind of visualization. Okay. How? चलिए अब इस कोड को देखते हैं. So I'm reading these three files simply: data, land, bbox, and graticules into three different variables: world bound, bbox, and graticule. I am creating the point from these from the list of points. So if you don't want to use these 3 points, you want to use some other points. So this is also a way, if you have points in an Excel sheet or a notepad file and you want to create a GeoPanda structure out of it, simply put it in an NumPy array and use these 3 lines of code to convert it into a GeoPandas data frame. Okay. So I'm running a loop for each of these points, converting them to a point class, and then using these city locations to convert it into a GeoPandas data frame. Okay. So these set of lines from line number 6 to 17 is used to convert any set of points into a point shape file kind of a thing. It is in a geo data frame right now. Next, I want to take these 3 data frames, world bound, bbox, graticule, and city location, and translate them into a different projection system. So these lines 20, 21, 22, and 23 basically translate these files, world bound, to another CRS. Now this is a way of writing a coordinate reference system. You could write a EPSG code. How many know what is an EPSG code? EPSG is, why am I not seeing anything? Oh. EPSG. EPSG stands for European Petroleum Survey Group, but that is not important. What is important is it has assigned a unique number to all your projection systems. So the one which you commonly use, called lat long in WGS 84 data, has the code 4326. The one which you use for Dehradun generally, 32644, is UTM zone 44N. Okay. Similarly, for each projection system, there is a code given. You don't need to remember all of them. There are hundreds of them. You would see the same code in your QGIS interface on the bottom right. You say it says EPSG 4326. That means this data which has been added is in WGS 84 lat long geographic coordinate system. So okay, I'll not go there, but there are multiple ways of specifying this. Okay, I'm showing you 2 ways. One is called the WKT format, or well-known text format. This is the WKT format. One is the EPSG format, which is this. So in a dictionary, you write INIT colon EPSG colon, then the code. So you could write 4326 or 3264 or whatever you want here and use this as a projection system identifier. So what I'm doing here is I have opened 3 files, created a 4th file, converted them to a Robinson projection system, and then I have simply plotted them. I have taken 2 subplots. So this means 2 rows, 1 column. These are the figure sizes. Let me reduce them. It becomes very big. Let me make them. The first plot has all the ones which are in 4326, that is in lat long, graticule, world bound, city locations. And the second one has all the ones which are in a Robinson projection system, VBox, Robinson, graticule, and so on. And the last part is simply for specifying that these numbers should appear like this and not as scientific notation, -5 e to the power 7. Normally we don't write grid numbers like this. So this last part is to ensure that these, if I comment this out, the program works, except that now you see the coordinates as -0.51 E7, which is not generally the recommended way of showing maps. So the takeaway from this is that you can convert any data simply by reading it, specifying to CRS and the target projection system. Now you could write a loop over all your files. Sometimes you need to reproject a lot of files. So about 5-6 lines of code and your job is done. Now let's come to the advanced part where we talk about some spatial analysis. I have given you some data called Ganga states. There are some states which I suppose forms the Indo-Gangetic plain, and I have taken these state boundaries. Again, these are not authentic state boundaries. The only authentic source of state boundaries for India is Survey of India. This is only for this demonstration. So I have taken these states, put them in a shapefile. This is in geographic coordinate system. It has attribute table. It has 2 columns. One is the name of the state, and there is another column which I have written as 0, which I'll tell you why later. So first thing which I want to do is dissolve all the polygons in a shapefile. Okay, so I have this shapefile, data / Ganga states. I open that, I print them, and I plot them. So this is how it looks here. These are the states in GeoPandas. Then we have a column called LSAD, as you saw, which has all zeros in it. So what it does, it resolves by column. So if you had a column which says wheat states and rice states, wheat and rice, then it would dissolve them as 2 polygons. So that is why I've created a column with all the same values. So on this column, when it dissolves all the polygons into 1. So I say states dot dissolve by this column, and if you print this variable basin, you will see that there is only 1 line. That means it is only 1 polygon, and this is how it looks. Okay, it looks nice. How do I save it? Simple, 1 line again. Basin dot, the variable name basin, dot to file, and then the name of the output file. So currently in the output file, I have a basin. Let me delete this. Although it is not required, let me delete this and run this again. And you will see that a basin shapefile has been created. Let us just open it in QGIS to see whether GeoPandas is doing correctly. And it appears to be doing correctly as it's supposed to. So it is dissolving all the states into 1 layer. Very easy, very simple. Now let us do more difficult stuff. Now let us do some intersection queries. So what is intersection? You take some input features, you put a cliff feature, and it should only give you the features which lie inside that cliff. So I have a file called populated places. This is a very big file. This is has all the populated places in the world. And I only want to see which ones lie in this small Ganga basin. Okay. So there are about 7,343 points, and I want to see how many of them lie in my basin, that is these points. Okay. So to do that, we read the populated places file and we say that there are 7,000 features. Let us plot both of them. So these are the points, and this small dark blue, let us make this face color is equal to black, comma, 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 comma. So this is the place where I want to see which points are lying. So how do I do it? I write a function and then I call this function for the two layers. One is places, one is basin boundary. And I see that it has selected all the features which are there inside my basin, which is 75 in number. Let us plot it and see whether it is giving the right answer. And I see that what was the name of that layer here? Basin, sorry. Okay, it's printing separately. My God, you have to create an access provided to both of them. Let's create an access, then provide the access to both of them. And now you have to make this transparent so that it is visible. So now what it is doing, it is simply clipping out features from a very large layer for the region of interest. Now this function is important and very long to explain. So you have to apply the operation to each geometry. So you say polygon.geometry.unary or union. Now what this is doing is it is applying this function unary union to each of the geometries in the polygon layer. And then you again apply the intersection. So it is very convoluted because this is how OGR is made. So instead of learning how this is done, use ready-made examples which are available on GeoPanda's site as well as OGR site, and write different cliff functions for line polygon, point polygon, and so on. The last thing which I want to show you is how to deal with more data. So I have two big layers. One is highways inside India. This is taken from OpenStreetMap, and this is not a lot of work has been done to reduce the size. It currently has some 9,000 lines, but actually the line layer of India is about over 700 MBs. I have reduced it down to 5 MB. So I have removed all the lines, only the primary highways, and a lot of attribute data has been removed. I think only one FID has been kept. There were 50 different other attributes. I have removed them to reduce the size. So my purpose to do this is to show you how to find out, let's say, which states have how much roads, okay? Or if you want to do some kind of analysis, let's say these days, this kind of analysis everybody is doing. You have Twitter feeds, geolocated tweets, and you want to know which states or which countries are giving more geolocated tweets. Similarly, if you have one spatial data, another spatial data, and you want to find out how many points are lying inside this polygon or how much roads are lying inside this polygon and all that. So we are taking two files. One is highway and one is states. I am reading them and I am plotting them first just to see what is the scale of data we are working. So I want to find out why in the the cumulative length of highway in each state. So the output should look like, okay, within JNK, these many kilometers, within Uttar Pradesh, these many kilometers. That is one output. Second output is find out state-wise road density. So maybe Jammu and Kashmir is very large, but the road data is only less. But for Delhi, if you see, the location is very small, but the data is a lot, or the roads are many. So we want to find out state-wise road density, that is length of road in kilometers by area in square kilometers. How do we do this? First, we do what is known as a spatial join. We join these two data sets. Now, again, this has many possible combinations are there. You can do inner join, left join, right join. Also, based on what, whether you want, these are based on topology, whether the lines are within the polygon or touching the polygon or crossing the polygon. So these two variables, there are 3 and 10 different possible combinations. You can go to these websites and you can see what they are used for and so on. There are many different binary predicates, contains, equals, and they are used for different things. Basically, all your spatial analysis, difference, symmetrical difference, clip, intersection, all are based on these two keywords only. So right now what I'm doing is I'm just joining the data such that I will get the name of the state for each line. So I am just showing, I did this operation, GPD, geopandas.spatial join these two layers, highway and states, and give me output in this variable called highway Ganga. The highway Ganga has many columns. I'm just interested in the ID, the name. So for each line, the name of the state has been appended to it. So you can imagine your line layer with an attribute table where each line, whatever is the name of the state, is appended to it. Now, if I plot this data based on this categorical, based on this name, okay, so I will see that these lines have been assigned these states to it. Okay. This has two variables. One is the states and one is the highway Ganga, that is the highways where the name of the state has been appended to it. This is good. Now we want to make measurements. We want to find out, this is visualization is fine, but tell me the length of the road which is inside UP. Now generally for doing distance and area measurements, your data should be in projected coordinate system. Currently the data is in geographic coordinate system. You see these lats and longs are in geographic lat long. So we want to convert it to a projected coordinate system. Which projection system will you use? For Dehradun, we use UTM-44. For India stretches across 6 UTM zones, starting from 42 to 47. So for an area as large as this, there is no single UTM zone you can assign to. Thankfully, NRSC has recommended one projection system. This is based on Lambert conformal conic, and so these are the details of it. And again, there is a corresponding EPSG code available, which is 7755. So we will use this directly to, so here it specifies the technical report for which this is given. So this is a valid projection system to use for all India kind of projects. So how do I convert? Again, same thing which I told you in the beginning, to CRS, INET, EPSG, whatever is the EPSG code. So this way I convert my highway Ganga and states to LCC, that is a projected coordinate system. And then how do I find the length of the lines? It is as simple as saying highway Ganga LCC dot length. This line will generate the lengths. This part here will add a column called road length, RD length, and assign those values. And this is where pandas comes in. Group by is a built-in function for pandas data frames. So what it does, it groups all the lines with the same name. Let's say Delhi, it will group all the road lengths and sum them together and print the output. So the output of this code here, this line is to restrict my decimal places to 4 decimal places. ये चला ही नहीं. So the output basically tells that for the state of Bihar, this is the entire road length in kilometers. Okay. Or meters, that I have to check. Anyhow, so this is the this is how you calculate or group different attributes based on a certain attribute. You could change this sum to mean, min, max, and all that. So this is a data frame. This is more of a pandas thing that we did. And we are working only on the attribute table now. Next, so this is the first objective, find the cumulative length of the road in each state. So from the data given, this is the cumulative length of the road. But how does it really match with the area of the state? So we find the area, states.lcc.area. This single line again, similar to dot length, generates the area. This is in meter square, so I'm dividing it by 10 to the power 6 to convert it to kilometer square. And now this is in a different file, which is states. This data is in a different file, highways. I have to merge them together. So I use another function called merge based on the name of the state. So let me run this. And now I see that I have a combined table where I have the state name, I have the road length, and I have the area in kilometer square. Now simply if I divide my road length by the area, which I am doing here, I get the length of the highway per unit area. And if I sort them based on this value, I see that Jammu Kashmir has the least amount of highways by area and Delhi has the maximum amount of road as compared to the area it has. So this is all I wanted to show in GeoPandas. There are many things you could do. The most of the things which I have shown you have been derived from this course developed by University of Colorado Boulder. And as an homework, you could trying out their their procedure on handling missing data. So if you have some missing data in your file, how do you fill it using GeoPandas? So this is what I wanted to show.